Okay, so we've looked at different integrals where the improper part has gone to either infinity or negative infinity or both at the same time. But what happens if we're not continuous somewhere on our interval? Well, when that happens, then what we're going to do is instead of looking at a situation where we change our integral to go from 0 to infinity and change that infinity to a b, what we're going to do is we're going to now approach that point of discontinuity from the left and from the right. So if we have a situation where that happens, then we just alter our integral a little bit and we change our limit a little bit to match the situation that we need. So if we're approaching a vertical asymptote, then we look at what's going on from the left and from the right, and we see if there's a limit that we can get out of that. So if you have a situation where we've got that, if we have that spot on the interval that we're interested in and it's discontinuous inside, then we have to break our integral up into two pieces. And this is similar to the improper integral that went from negative infinity to positive infinity. Okay? Well, that's exactly how we start with our first example here. We've got the integral from 0 to 3 of dx over x minus 1 to the 2/3 power. The problem is, if you look at x minus 1, that equals 0 when x equals 1. That's on that interval between 0 and 3. So what we have to do is break this guy up into two separate integrals. And we're going to look at the integrals this way. We're going to look at the integral from 0 to 1 of dx over x minus 1 to the 2/3 power, plus the integral from 1 to 3 of the same thing. Okay, and so what we do with this situation is now we go, okay, we can't really put a 1 in here at all because that gives us an undefined situation. We can't put 1 in here because that gives us an undefined situation. So we look at the limit as x approaches 1 from the left, okay, because we're on the left-hand side of that. And actually, I'm going to take that x off and make it a b. So as b approaches 1 from the left, and then we can look at our integral now from 0 to b of dx over x minus 1 to the 2/3. Okay. On the flip side, over here, we would have the limit as c approaches 1 from the right, because now we're on the other side of that guy, of the integral from c to 3 of the same thing. Okay, and we're gonna add these two guys up. So this is what we're working on. This is the thing that we're going to integrate. And we really just need to integrate it one time. Now, we have to handle our 0 to b and our c to 3 parts separately. But basically, what you're integrating is, if we just think about this in general terms for just a second, I'm integrating the integral of, watch this now, x minus 1 to the negative 2/3 power dx. Okay? And with that just one x in there, all we have to do is add 1 to the exponent and divide by the new exponent. Okay, that's all we have to do. Now, if this said 2x, we would have to do a u substitution. But on this guy, what we're going to end up with is x minus 1, and then add 1 to your new exponent, which makes it the 1/3 power, and divide by 1/3. So remember, when you take that step, you're actually multiplying by the reciprocal. So both of these integrals are going to pop out as 3 times x minus 1 to the 1/3 power. Both of them do. Now we just have to do the math part, which is stop minus start. So I'm going to have to get creative with my space. I didn't leave myself a lot of space to work here. So what we'll do is we'll take this guy and we'll work him over here. So I'm looking at the limit as b approaches 1 from the left of, and then my integral, which is going to be 3 times x minus 1 to the 1/3 power, evaluated from 0 to b. So I do stopped minus start. That's going to be 3 times b minus 1 to the 1/3 power minus 3 times 0 minus 1 to the 1/3 power. So the cube root of negative 1 is negative 1. So negative 3 times negative 1 makes that positive 3. All right. And then as we get close to 1 here, okay, remember we're approaching 1. Well, I can put a 1 in for this guy. And 1 minus 1 is 0. So this is going to be 0 plus 3. So the first limit goes to 3. I'll do the second one right here. I think I'll have just enough room. That's not a different enough color. So the second guy is going to be the limit as b approaches 1 from the right of the same thing, which is going to be 3 times x minus 1 to the 1/3 power. And now we're going to evaluate this, though, from c to 3. And so when I do that, I get 3 times stop, which is going to be 3 minus 1 to the 1/3 power, minus 3 times where I started, which is c minus 1 to the 1/3 power. Okay, so 3 minus 1 is 2. So we're looking at the cube root of 2. Well, I don't know what that is, but I'm going to multiply it by 3. So I got 3 times the cube root of 2. And then when I put a 1 over here, that's going to be 0 again. 1 minus 1 is 0. Cube root of that is 0. So there's my second part. All right. So what do? I add these two guys together. And when I add my first part, when I add this with this, that will give me the answer to my problem. So what is my answer going to be? My answer is going to be 3 plus the cube root of 2. 3 times the cube root of 2. So there's a few steps in here, but again, it's using those same properties of limits that we used on the other improper integrals that we were talking about on some of the previous slides. So just be patient, use what you know, take advantage of the things that you know. When you can substitute a 1 in and get a real number like 0, that's fine. But if you have a situation where you have an indeterminate form, look for L'Hopital's rule. But one step at a time here, one algebraic step at a time, and the calculus will take care of itself. All right, the second situation we have here now more strongly resembles one of these first two parts. We've got the integral from 1 to 2 of dx over x minus 2. And if you put the 2 down here in the bottom, that's where we're going to get our 0. So we can't use that 2 as part of our limit. That's what makes it improper. And we're approaching the 2 from the left. And so the setup then for this guy is going to be the limit as b approaches 2 from the left of the integral from 1 to b of x minus of dx over x minus 2. And this is also a situation where we're going to have to take an integral. And because the x part is just x, it's not 2x or x squared or 3x or something like that. When we take this integral, it's just the straight up natural log. It's no different than looking at the integral of 1 over u times du. It's going to be the same thing is going to happen. Okay, this guy becomes the natural log of the absolute value of u. Okay, the same thing here, because when you take derivative of x, you just get 1. So our limit then is going to be b approaches 2 from the left of the natural log of the absolute value of x minus 2 evaluated from 1 to b. And it's stop minus start. So this is going to be the natural log of the absolute value of b minus 2 minus the natural log of 1 minus 2. Okay, and so when we sort this guy out, what we're going to end up with is The natural log of 1 minus 2, the absolute value of that, well, that's 1, right? Because the absolute value of negative 1 is 1. So you get the natural log of negative 1. Absolute value of that is 1. The natural log of 1 is 0. So that just leaves me with this guy over here, the natural log of b minus 2. Well, 2 is approaching, I don't know why I wrote a minus 1 here. We're just coming in from the left. 2 is approaching from the left. In other words, we're at like negative 2.00001, negative 2.00001, negative 2. Blah, 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 blah. And so what's going on here is we're getting really, really, really tiny numbers. So we're looking at the natural log of the absolute value of a really small number in here. So I'll go ahead and write this out. Let me move that a little bit. So we would say minus this. Okay, and then think about what's happening with your natural log in this case. As we get smaller and smaller numbers here, okay, we get closer and closer to 2, then the numbers inside the natural log are very, very small. And small numbers inside a natural log actually approach negative infinity. So if you get your calculator out and you punch in natural log of 0.0001 and get an answer, and then do the natural log of 0.000001 and get an answer, what's going to happen is this guy right here approaches infinity, negative infinity. Okay, and so we would say that this particular integral then would go to negative infinity. And since it goes to a negative infinity, we can say that it diverges. It doesn't converge on a specific number value. So there you go. There's another improper integral situation. Again, the math is not hard for this particular one. The algebra is not too bad, but you do have to be aware of what's going on with natural log as you're really close to 0. All right, on this particular example, we want to look at a comparison test. So we're going to have two functions that we're going to compare, f and g. Let me choose a highlighter here. So here's f right here, here's f right here, and here's f right here. We're going to compare f with g. And what we want to do is we want to notice some different things. And then based off of those different things, what can we make an assumption with about our integral, okay? And so first off, if we have to set it up this way, 0, number one, we've got to be bigger than 0, but f needs to be less than g, okay? It's got to be squeezed in between 0 and g. So if g converges, because f is between 0 and g, it also will converge, okay? So if f is smaller than g, but g approaches a specific value, a specific point, a specific horizontal line, then f will as well. On the flip side of that, if f of x diverges and goes to infinity or doesn't approach anything specifically, since it's smaller than g, g will also diverge, okay? And those can be difficult concepts to think about, but think about a graph. If we were to have a graph of a situation where on the convergent part, if I drew f of x here, and if I drew g of x here, and I told you that f of x was less than g of x, well, my pink line is going to go wherever that purplish line goes, okay? They converge. On the flip side of that, if I take my f of x line, and I say that it's less than g of x now, and it does something like this where it approaches infinity. Well, remember, he's less than g of x. So g of x would also then approach infinity, okay? And so that's kind of how this is working. So here's the question. Does the following integral converge? So they give us 1 to positive infinity of e to the negative x squared dx. Well, let's set this guy up. This would be the limit as b approaches infinity of the integral from 1 to b of e to the negative x squared dx, okay? Looks a little bit on the gross side. So what we're going to do is we're going to let e to the x squared be equal to f of x. So we're going to say f of x equals e to the negative x squared. we want to pick a function that's bigger than that. And so the one that we can pick that's bigger than that we can use for comparison is one that's really similar to that as well. So we could say, hey, what about if we picked e to the negative x? Okay, if we can show that e to the negative x converges, okay, if we can show that this is true, that this statement is true right here, that e to the negative x converges, then since f is smaller, f would have to converge as well. So what we want to do is we want to change our limit and take it from this kind of nasty, gross-looking guy to this one. We're going to look as b approaches infinity, and we're going to look at the integral from 1 to b, but now we're going to look at e to the negative x dx. And if we can show that this guy converges, then we can say that our blue guy converges as well. So here we go. The limit then, when I integrate this, that gets me negative e to the negative x evaluated from 1 to b. And again, that's going to be the limit as b approaches infinity. So stop minus start, negative e to the negative b minus negative e to the negative 1. Okay. Well, keep in mind with these e's, anytime you see a negative on the top, you can always put it on the bottom to get a positive exponent. So this is actually going to be negative 1 over e to the b plus 1 over e to the first. So it would just look like this. Well, notice that when b goes towards infinity, okay, right here, then this part is going to go to 0. The reason is the number on the bottom gets larger. The number on the top never moves. And since the number on the bottom gets larger and the number on the top never changes, then we would approach 0. That leaves us with a limit of 1 over e, okay? That's a convergent function, okay? This function converges to 1 over e. So since this guy converges, the f of x part, this one also converges because he's smaller than the one we checked. So we would say that this integral converges to a specific number. And that's all you do for the comparison test. It really is just that easy. Okay, we're going to use the arc length formula to show that the circumference of the circle x squared plus y squared equals 4 is 4 pi. So let's get some things that we can work with here because we don't necessarily want to work with a super nasty function. If I were to graph this circle, it's got a radius of 2. So it comes out here to 2, comes up 2, comes over here 2, and it goes down 2. Okay? And so if I draw this circle, which it's not very good, so sorry. Oh, that's horrible. Let me try again. So football circle. That's not too bad. Okay. So basically what I can do is this. What if I look at just the part of the circle that's here in first quadrant? Just this part right here. Okay? The x values that we're running through go from 0 to 2. Okay? And so if I just look at that one part, that would give me this one little teeny tiny piece. Okay? The reason that I want to look at just this one little teeny tiny piece is that when I set my equation up and solve it for x, I only have to deal with the positive square root part. Okay, remember we're trying to solve for y, so we would have y squared is equal to 4 minus x squared, and then I take the square root of that. So the square root of 4 minus x squared is the equation that I would use to graph this. But we're only looking at the positive part, and we're only looking from 0 to 2. So when I set my equation up here, I can look at just the function y equals the square root of 4 minus x squared. Or y equals 4 minus x squared to the 1/2 power. Okay, so one of the things that we're going to have to use is our arc length formula. And arc length says that, length, we'll just use length, is equal to the integral from a to b, in this case 0 to 2, because that's the only part that we're looking at, times the square root of 1 plus y prime squared. All right, so I need to figure out what y prime is. Back to this guy right here. Y prime is 1/2 times 4 minus x squared to the negative 1/2 power. Okay, that's the derivative part. Now I have to chain, because whenever you take derivative and you have stuff in the inside, then you've got to chain that stuff out. And so that would give us then times negative derivative of 4, 0, okay, derivative of negative x squared, negative 2x. So I can simplify my problem a little bit, and y prime becomes, the 2's cancel, and I end up with negative 1 over 4 minus x squared to the 1/2 power. Okay. All right. Not too bad. So let's put this into our arc length formula. Our arc length then is going to be the integral from 0 to 2 of the square root 1 plus the derivative squared. I'll go ahead and write it in here, negative 1. Oh, whoops, that should be an x up there. Let's see here. This should be a negative x, not negative 1. So this guy would be negative x over 4 minus x squared to the 1/2 squared. Oof, that's really big. Okay, go ahead and simplify this one step. This would be 1 plus, and then negative x squared is positive x squared. And the square root of 4 minus x squared is 4 minus x squared. So I wind up with this fraction right here. Now, what we want to do is we want to try and get to 4 pi. So in this situation, normally I would say, hey, use your calculator. But if we're looking for a specific value of 4 pi, that's not really a calculator phrase. So what we're going to do is get a common denominator here and combine these fractions together and see if there's a way to maybe clean this guy up and get something that I can use. Okay, so this side needs 4 minus x squared. This side just needs 1, so he's all good. And what we end up with then is 4 minus x squared plus x squared. And we wind up actually dealing with 0 to 2 of the square root of 4 over 4 minus x squared. Now, don't panic a lot at this point in time, because you're looking at this thinking, how in the world am I going to integrate this? By the way, there should be a dx back here and a dx right here. Don't panic. Notice that if you have your trig sheet, or if you have a sheet of different integrals, run through the arc inverse trig integrals. And you'll notice that this guy right here strongly resembles, he's not quite ready for it yet, but he strongly resembles the arc sine function. So what we need to do is get it into a form that arc sine can be used. Okay, so back up here to the top, we're looking at the integral from 0 to 2. And I'm going to do a cool trick here. I'm going to factor a 4 out from everywhere. Okay, and if I factor the 4 out, what that does is it cancels the 4 on the top and the bottom. All right, but this is going to be a really little bit on the unique side. The ones okay? 4 divided by 4 is 1. Okay, 4 divided by 4 is 1. But 1 divided by 4 is 1/4. Okay? So all I did was factor out a 4. I kind of left out that little basics factoring step, but it looks like this. Now, 1/4 x squared, 1/4 x squared is equal to x over 2 squared. And this guy right here is what allows me to get to the arc sine. Okay, so watch my next step. I'm going to have 0 to 2 of the integral of 1 over 1 minus x over 2 squared dx. This guy right now, this is what the arc sine looks like. Okay, that's what the arc sine looks like. So what I do is I integrate that out and then times the derivative on the inside. So now back over here with all my limit process stuff, I'm going to look at the limit then. Well, let's do this. Let's do this. Let's go. When I integrate this, I'm going to have the arc sine of x over 2. Okay. And so what I want to do is I want to look at a way to find the total length of everything now. Okay. And so I need to keep in mind that I'm doubling all of that. All right. So what happens is I'm going to have a 2 here. Okay, 2 in front, and I'm evaluating it from 0 to 2. Okay. Now this all looks well and good. The problem is when we go back to our setup here, this guy right here. This guy right here tells us we're going to have an improper integral. And the reason he tells us that is because any value that's equal to 2 cannot go in there. So what we're going to do is we're going to set up our limit as b goes to 2 from the left, and then we're going to change this 2 right here to a b. Okay. So there's your setup on this guy. Doesn't look too bad, right? All right, I'm going to finish the problem down here under Gabriel. So to finish off this problem, what we're going to do is we're going to put our stop minus our start in. And that's going to give us the limit as b approaches 2 from the left of 2 times the arc sine of where we stop, which is b, minus the arc sine of where we start, which is 0. Okay, and now I can put the 2's in here because it's going to be all right. And this needs to be arc sine. All right, so what angle gives us a 0? Okay, what angle gives us an arc sine of 0? Well, 0. Okay, and then on this guy right here, I'm going towards 2. So what I have is b over 2. Well, I can substitute this 2 into this spot. So what angle gives us the sine of 1? And in this case, it would be a pi over 2. Okay. So what I'm going to do is I'm going to have 2 times this guy, which is going to give us pi. Okay, I misspoke right here. I want to come back to this guy for just a quick second. When we do this, when you look for your arc sine, that's going to be 1 over 1 minus u squared. Okay, that's the arc sine setup. So in this case, my u equals x over 2. So du equals 1/2 dx. When you solve that for the dx, you get 2 du. That's where this 2 came from. So when we sort it out, this pi right here is the length of this one part of the circle. So pi is that length right there. Well, I've got 4 of those. So when I do this times 4, I get 4 pi. And there you go. Hey, that's cool. We just used calculus to solve a geometry problem. All right, last question. Finding the volume of Gabriel's horn, or finding the volume of the graph y equals 1 over x. Now, what's interesting about this is y equals 1 over x is really interesting. It's a graph that looks something like this. So on one side, we go towards infinity, and on the other side, we go towards infinity. So we're going to make this one tiny, teeny step easier. And we're going to say, hey, we're going to go from this point right here that way. So can we find the volume of this shape? Well, we're going to rotate this shape around the x-axis, and when we do, we get a circle. The area of a circle is pi r squared. R in this case is 1 over x. So when you solve this guy out, when you set this integral up, it's going to be improper because we're going to go from 1 to infinity of pi times the radius squared. Well, what we're going to do then is we're just going to use our rules of impropers. We're going to let b go to infinity, and we're going to look at the integral from 1 to b of, now watch this here, pi over x squared dx. Okay? So when you integrate this, remember this is actually x to the negative 2. So this is like saying that we're integrating from 1 to b, pi times negative x to the negative 2. So when I integrate that, I add 1 and divide by that new number. That's going to get me pi, negative pi over x. And we're going to evaluate this from 1 to b, and we're going to take the limit as b goes to infinity. Okay? Stop minus start in this situation. So we're stopping at b. All right? So negative pi over b minus negative pi over 1. And as b goes to infinity, the pi never changes, and this guy goes to 0. All right? And so what happens is the area under this curve, which is referred to, believe it or not, as Gabriel's horn, so this area right in here, actually has a finite volume. And that finite volume is going to be positive pi. Because when you look at the limit, we're going to look at the limit as b goes to infinity of negative pi over b plus pi. Pi is a constant, so as b grows larger, pi never changes. And since pi is a constant, as b grows larger, this number right here, this guy, he grows smaller. So there you go, Gabriel's horn. We can find the volume going from 1 to infinity. Now here's the question. Can we find the volume between 1 and 0? Maybe that's something that we can do in class.